Hello and welcome. Today we are going to be discussing the problem sliding window simulation. In this problem, we are given an unknown binary string b, and we want to know what are the minimum and maximum possible number of ones that could occur in this unknown binary string. And in order to work this out, we are given several constraints of the form Ri, where Ri is going to be the sum of all of the values from Bi up to Bi plus k minus 1. This is just a fancy way of saying the sum of k consecutive elements starting at Bi. If you want that in math, it's going to look like this, and we're taking that sum mod 2. So the values of Ri are also binary numbers. They're either 0 or 1. And we want to use these values of Ri in order to work out what can be B. And the key observation in this problem, and this is a very mathy question, is that we can produce a formula like this, where the value Bi plus k depends on the value of Bi and the known values Ri and Ri plus 1. So what's so nice about this formula is that there are two unknown values and two known values. So that means once we fix the value of Bi, then that allows us to directly compute the value of Bi plus k. And then using the value of Bi plus k, we could continue on and compute Bi plus 2k, Bi plus 3k, Bi plus 4k, and so on. So this allows us to calculate what is the bit that is k places away from my current bit. So where in the world did this formula come from? Because it definitely wasn't given to us by the problem statement. We have to do a little bit of math here. So the math is going to start off by adding two consecutive values of Ri together. So we're going to have Ri and Ri plus 1. And we're just going to apply the definition of Ri. So we have Ri here, and we have Ri plus 1 here. And most of the elements in these sums are identical. So what we're going to do is we're going to pull out the elements that are not the same. So from the value of Ri, we are going to take out the value Bi. And from the value Ri plus 1, we are going to take out the largest value, which is Bi plus k. And in doing so, what we are left with are two sums that are actually identical. So if we take a look at these values highlighted in orange, we're going to see that those orange terms are literally the same sum. So since they're the same sum, another way of writing this is simply 2 times that sum. But if I have 2 times any term when I'm taking the expression mod 2, that term just disappears, right? Because it's a product of 2, so it's always going to be 0 mod 2. So that just leaves me with the values Bi plus Bi plus k. So if we rearrange terms here, we can end up with equation 1, where Bi plus k is expressed as the sum of Bi, Ri, and R of I plus 1. So as soon as we choose that value of Bi, every k values after it has been fixed in place. And what this allows us to do is this allows us to determine how many ones and zeros are going to be in the string if I choose a certain bit for the first bit, or what happens if I choose a certain bit for the second bit. It'll determine not just one bit, but actually a whole sequence of bits. We are now ready to begin forming a solution. The most important thing from the left-hand side of the screen here is that formula in green. Once we choose a value for Bi, it determines the value for Bi plus k, which then can be used to determine the value for Bi plus 2k, and so on. So once we fix a bit at the beginning of this string, it doesn't just determine one bit, it actually determines a whole sequence of bits. So what we can start by doing is we can set the first bit, B0, to 1, and then we can see what bits does that generate throughout the string, and we can determine whether or not setting B0 to B1 was a good choice or a bad choice. Now, the words good choice and bad choice depend on whether or not you're trying to minimize or maximize the number of ones in the string. So for now, let's just assume that the problem wants us to maximize the number of ones. So more ones is good from the perspective of maximizing the number of ones. So we're going to fix B0 to 1. Again, that's an arbitrary choice. We're going to see if that choice ends up being a good choice or a bad choice. So this determines BK, B2K, B3K, and so on, again, using that formula on the left-hand side of the screen. Then, once we have all of these numbers, we can count the number of zeros and ones in this set of bits. How many zeros occur, how many ones occur. If there are more ones than zeros, then assigning B0 to 1 was a good choice. So that is the maximizing choice. We ended up with as many ones as possible. If, on the other hand, we ended up with more zeros, then assigning B0 to 1 was a bad choice. We want more ones than zeros, so it would have been better to assign B0 to 0. Because if I change the starting bit, then every single bit afterwards flips. So anything that was a 0 becomes a 1, and anything that was a 1 becomes a 0. So what this allows me to do is simply determine what is the optimal value for B0. If there are more ones than zeros when I assign it to 1, then the optimal value is a 1. Otherwise, the optimal value is a 0. And what I can do is I can repeat this same process for B1, B2, all the way up to BK minus 1. And I only have to go up to BK minus 1 because, again, BK has been determined by B0. So I don't need to go past BK minus 1. I only have to check this for the first K elements of the string. And what I'm going to do for each of these independently is check, is it better to assign 0 or is it better to assign a 1? And because I can solve each sort of set of bits independently, I don't have to worry about brute forcing over all possible assignments, right? Because if I brute force over all possible ways to assign values to B0 to BK minus 1, that would be exponential in time. The key thing here is that I'm doing each test independently. I'm thinking what's optimal for B0, then I'm going to think what's optimal for B1, what's optimal for B2, and so on. I don't have to sort of check any interaction between the bits. They're all independent of each other. There is one edge case that we have to watch out for. Because we are assigning the first K bits independently and choosing sort of what is the best value, there could be a small problem where when we choose the optimal values for these first K bits, we could end up violating the constraint for R0. And just as a quick reminder, remember that the constraint R0 is the sum of the first K bits mod 2. So it could be that these K bits, when we choose their optimal values, don't actually align with this R0 value. And in that case, the solution is we just simply have to flip one of the bits in this set. And the best bit to flip is the bit with the smallest difference in its 0, 1 counts. So some of these bits might have a lot of ones and very few zeros. That would be a very bad bit to flip because it's going to hurt us. We're going to lose a lot of ones when we flip that bit. But if these values are actually very close to each other, or perhaps even equal to each other, then changing one of the bits into a 0 or a 1 won't hurt us. So we want to flip the bit with the smallest difference in its counts. So far in the code, we have simply read in the input, nothing exciting's happened. The next thing we need to do is initialize some variables that are going to help us store the data we need to complete this problem. We're going to start off with the array assignments. This is a length K array storing the optimal bit assignments for the first K bits in the maximum case. So again, we're solving the problem from the perspective of the maximum case. When it comes to the minimum case, the negation of assignments will be the best thing to do. So whatever we do for the maximum case, the opposite is what we want to do in the minimum case. We're also going to store what is the total minimum number of ones, the total maximum number of ones, and this min difference variable. Again, the min difference is simply the minimum difference in the counts between zeros and ones for each of the starting bits, so that if we do end up having to flip one of them away from their optimal value, we can do the bit that is least harmful to us. So going on here, we are going to loop over the K starting bits and work out how many zeros and ones are produced when we assign 1 to that starting bit. So when we say x equals 1 here, you can think of this as assigning bi to 1. And we're going to check if I assign bi to 1, how many ones do I produce? How many zeros do I produce? We're going to create counts to store that. So count 0 stores the number of bits assigned to 0. Counts 1 stores the number of bits assigned to 1. Note that these 1 slot starts off with a 1 here because we've already assigned the first bit in the sequence to be a 1. So we always start with a 1 here. And then we are going to loop over every single bit in the sequence. For those of you who are not familiar with the range function, if you're coding in C++ or Java, this k in the third slot here is a skip count. So what this loop is doing is it's starting at the value I, and then it skip counts by k. So it goes to I plus k, I plus 2k, I plus 3k, and so on, just like our sequence here was doing. And we're going to check what happens to the value at bj. So we're going to apply our formula that we had on the screen from earlier. Again, it's just the old value of bi plus rj plus rj plus 1. Mod 2 is going to give us the new value, the next value of bk. Again, another way of thinking about this is that if rj and rj plus 1 are the same, then the value of x remains unchanged. If, however, rj and rj plus 1 are different, then the value of x must also change. So now we can just increase our counts at x by 1. So if x is a 0, we found another 0, so the 0 count goes up. If x is 1, we found another 1, so the 1 count goes up. And at the end of this process, what count stores is the number of zeros in this set and the number of ones in this set. So that allows us to very easily calculate min difference as simply the absolute difference between counts 1 and counts 2. And we're only going to update min difference if this is smaller than any difference we've seen before. So we're starting min difference as some arbitrary large value. And then as we see smaller and smaller differences, we are going to end up with smaller and smaller values for min difference. Then what we're going to do next is we're going to check, was it actually a good idea to assign x to 1, right? Should I have set the first bit to 1 or the ith bit to 1? And we said that was only true if the number of ones ended up being bigger than the number of zeros. So if the number of ones is bigger than the number of zeros, we say that assignments I is 1. It was a good idea to set the ith bit to 1. Otherwise, if this is not true, the best thing to do was set the ith bit to 0 like we have originally. Then we're almost done here. We're simply going to increase maximum by the maximum value in counts. So whatever is the larger value in counts is the number of ones I can obtain from this particular sequence. And we're going to increase minimum by the minimum value of counts. So that's the lowest amount of ones that I can obtain from this sequence. And then we could at this point just print out minimum and maximum, if not for this edge case. We have to make sure that when we chose all of these k bits, they satisfy the very first constraint of R0. So what we're going to finally do here is check if R0 is satisfied. And there's sort of two different formulas here. So we're here first checking if R0 is equal to the sum of assignments mod 2. So this is just the sum of the first k bits. And that if that's not true, right, if these don't match, then we have to subtract min difference from the maximum. So the maximum is a little bit smaller than we would have hoped it was. The formula is a little bit different from the minimum because we're taking the negation of assignments. So instead of doing sum of assignments, we are doing k minus the sum of assignments, which is the same as flipping all of the bits in assignments and then taking the sum. So again, if that doesn't match R0, then the minimum is actually going to be a little bit higher than we hoped, right? So we lost one of our optimal values. And then finally, we print out the minimum and maximum, and that completes the problem. So very mathy question here, but also a very nice and satisfying solution. We can improve the sort of exponential brute force runtime by analyzing each of the first k bits independently. And that's the key observation. So thank you so much for watching and have a wonderful rest of your day. Bye-bye.